I know I said this was a u-sub video, and it is, but I can't help myself. I have to talk a little bit about just what an integral is first, and maybe you'll get some use out of it. All right, so, or actually let me backtrack even further and give you a 15-second review of what a derivative is. Mostly just because the notations, we're going to steal part of it. So, basically the idea with the derivative is you take delta y, you divide that by delta x, but then obviously the derivative, the idea is to find the instantaneous rate of change. So instead of looking at the rate of change over this whole region, you're going to shrink that region down to 0, so you're really just looking at the point and the immediate vicinity of that point. So what that means is you take the limit as delta x approaches 0. And then because, you know, it's a limit is basically just taking this number and getting right up close to the value you're approaching and stopping just short of it. What we're doing is we're stopping just short of 0. So in effect, delta x and then delta y along with it become basically infinitesimal. Mathematicians will yell at you, but in effect that's what happens. And so to denote that, instead of using a delta, we're just going to use a d. A d meaning infinitesimal change rather than finite change. So dy over dx instead of delta y over delta x. Okay, keep that in the back of your head. So there's a lot of different reasons you would do an integral. So I feel like I would be giving too much weight to any one reason if I actually picked one motivation and then showed what you would do and then derived an integral from there. So I'm just going to give you what an integral does, and then I'll show you a couple different reasons that you would do an integral. So an integral is basically, the basic idea is you're going to take a sum from x equals a to x equals b, and we're summing f of x times a change in x, delta x. So if my a is 1, my b is 3, and my delta x is 0.2, just to pick a random example, then what I'd be doing is I'd say, f of 1, because we're starting at 1, and I'd multiply that by my delta x, which is 0.2, and I'd plug in 1.2, multiply that by 0.2, add 1.4, multiply that by 0.2, etc. Take that sum, and then you just take the limit as that delta x goes to 0, as those intervals get smaller and smaller. So then your delta x becomes a dx, and to denote this sort of infinite sum of a kind, we change from a sigma to an s for sum, and we just, to make it look cooler or something, I don't know, we squish the s this way, then we stretch it out this way, so you get this shape. But then, obviously, you're still summing from x equals a to x equals b, and you're still summing f of x times a change. The only difference is, instead of a finite change, it is an infinitesimal change, basically. So you use dx instead of delta x. What if f of x is actually the rate of change of some other function, capital F? Well, then what happens is this integral, this sum of f times a tiny change, starting at a and ending at b, simplifies a bit. And the way that does that is basically, and notice I'm just subbing in df dx, d capital F dx instead of f of x here. Basically, mathematicians will yell at you if you say this, but the effect is the same. This dx and this dx just cancel. Boom. So then all you're left with is you're summing up all of these tiny changes in f, capital F that is, starting at a and ending at b. So then obviously if I'm just summing up all of these tiny changes in f, then what I get is my total change in f over that range. So this just becomes capital F at b minus capital F at a. Or delta f if you like, actually. I'm gonna write that just for fun. That's usually how you're going to compute this integral, is by finding an antiderivative of whatever this f function is, and then just finding the total change over this interval. There's a few different reasons you would do that. Number one, what if I gave you f of a, capital F of a that is? Well then, you know what the change is from a to b. So if I gave you capital F of a and you knew the derivative of capital F, you could find f of b using the derivative and the starting value. You could also interpret this, and I think you've talked a good bit about this, so I won't elaborate too much on it, as being a sum of, let's go back here, a sum of base times height, right? Your height is f of x, your width is this tiny change in x dx. So in effect, you get this rectangle with height f of x, and then you're doing that at every point from A to B. So if you summed up the areas of all these rectangles, of course, you would get the total area under the curve. So that's another reason, is if you wanted to find area under the curve. And just to give you a fun example of a third reason why these integrals might be useful. Let's say I want to find the area of a circle with total radius capital R. Then what you could do is you could take a circumference. You could give that circumference a very, very, very small width. Very, very small width, which is equal to basically some tiny change in the radius. So then the area of that tiny guy, tiny bit of area, I'm just going to denote that by dA, would be 2 pi r, whatever this little r is however far out we are at this particular moment. And then that would be multiplied by your tiny change in r, which is basically the thickness of that circle. And then what you could do is you could then find the total area by summing up all of these infinitely many little tiny little thin rings of area 2 pi r dr, starting at r equals 0 and ending at r equals capital R. And then hopefully you're familiar with how you would find the antiderivative of this. You would raise the power of that r to a 2, then divide by 2. The pi just kind of comes along for the ride, so you get pi times r squared. You would plug in capital R, and then you subtract and you plug in 0. So altogether you just get pi r squared. Okay? It's pretty nifty. So then u-sub, what the video is actually about. The idea behind u-sub is basically, what if I'm integrating something called, it doesn't really matter what's in the integral. I'm just going to say maybe that's a thing times another thing, which in this instance I'm going to call f of x times g of x. I'm trying to anti-differentiate that with respect to x. And I'm looking at that, I'm like, how the heck do I do it? It looks kind of crazy. Well, here's the trick. We're going to do something not too dissimilar from when I said, what if f of x equals the derivative of some other thing? I'm going to say, what if that g of x is actually the derivative of some function u? And what if my f of x I can rewrite in terms of u as just some h of u. So then my integral becomes, well, here's du dx, that's the same as g. So what happens? Effectively, those dx's cancel. And so I can rewrite this as going from x equals a to x equals b. And, f of x I'll just rewrite in terms of u. And then what I have left is du. And so basically, I have rewritten the same integral as a different integral, but that will give you the same number if you work it out. And if we're lucky, this is much easier to evaluate. One quick side note here about anti-differentiation, just in general. Here's why. Part of why we steal the notation to talk about an antiderivative. We do that because you could kind of think about that as, well, what if I just made this bounded and I just go from, any x value that I want to. I'm just going to say like x equals a, but then I just end at x, just a generic x. And then I'm integrating f of x with respect to x. So then let's say the antiderivative of f is capital F. Then I'm just summing up all these changes in f, starting at a and ending at x. So then I get capital F of of x minus capital F of a. But then if I'm just trying to find the antiderivative generically of this function f, really I'm not confined to having this number be f of a. It can be, you know, whatever it wants to, and it's going to go away when I differentiate again. If I want to differentiate and get back to little f, then obviously this guy becomes little f, and then any constant I had here, not just a value that you could get by plugging into capital F, is going to go away. And so really, I could just add any constant I want to, and collectively call all of this C. That's part of why we steal the notation, and that's also why u-sub still works for an indefinite interval. For those who are interested. Okay, let's actually do some practice problems. So let's start with the antiderivative of pi sine of pi times x with respect to x. So we're just looking for a function in terms of u multiplied by what the derivative of u would be. In this case, the move, if you see it, is to go, well, the derivative of this guy would get me just pi, and then I got a pi out here. So what if I say my u is that pi times x, and then my derivative of u is that pi. So du dx instead of pi, and then I get u instead of pi x, and then that's times dx. So then, in effect, these cancel, and what I'm left with is the integral of sine of u with respect to u. And so then if I were to work that out, of course, the function that gets you sine when you take the derivative is going to be negative cosine, and then you can add any constant you want to. So really, you're going to get negative cosine of u plus any constant c that you want to. And then you're always going to want, with these u-subs at the end, to go back to your x's instead of your u's. So I'm just going to plug in what my u is, which is negative. So it's going to be negative cosine of pi x. And then plus that constant c at the end. All right, so what if I want to anti-differentiate x squared times x cubed minus 1 to the 4th? I'm looking at this and I'm seeing a power lower than what's in here. So what if, could I get this as my du dx, and could I get this as my u? I don't know, but it's worth a shot. So let's see. All right, so let's say u equals x cubed minus 1. Part of this, really, with u sub, there is some strategy to it, obviously, but part of it is just guesswork, more or less. So let's say my u is x cubed minus 1. Take the derivative of that. My du dx is going to be 3x squared. The 1 goes away because it's a constant. And then I'm looking up here and I'm seeing, okay, so this becomes my u. This is not my du dx, but it's off by a constant. And because an integral is just a sum, you know, how I could do like 3, let me do it down here. Let's say I did like 3 of a plus b plus c plus etc. equals 3a plus 3b plus 3c plus 3 times everything else. In the exact same way, because an integral is just a sum of all of these different values of this function multiplied by dx, if I took any constant, you know, k, let's say, and then I did some kind of integral, and let's say it's from x equals a to x equals b like usual, I could just sum up k times f of x times dx. And that will give me the exact same thing. And so what that comes down to, you know, when you're just doing the quick algebra, is you can just, if you have a constant, you can pull it out, or you can put it in. You can put it on either side of that integral, it doesn't really matter. So, all that to say, I don't have a 3 here, but what I could do is make a 3, more or less. So, what I could do is I could multiply by 1/3, and then multiply by 3, which is, obviously that changes now. I guess just multiplying by 1 is the net effect there. But if I had the 1/3 on the outside, and the 3 on the inside, well then, now I'm seeing my du dx and my u. And so then I could just plug in, that's 1/3 du dx times, oops, I forgot my power right here. Should be u to the 4th dx, and these dx's basically cancel each other out. So what I'm left with is 1/3 the antiderivative of u to the 4th with respect to u, which that is 1/3 times u to the 5th over 5 plus any constant that we want. Because this is any constant that we want to, what I'm going to do is I'm going to distribute this 1/3. And well, let me start on the first term. That's u to the 5th over 15. And then plus, and I could write c over 3 if I wanted to, but any constant over 3 is still, I could still have that be any number I want to. So I'm just going to leave that as c. You could think it kind of gets absorbed into the c, just because c is any number you want to. So if it's multiplied by 1/3 or not, it doesn't matter. All right, so u to the 5th over 15 plus c, and then just to not leave things in terms of u, plug back in. So u equals x cubed minus 1 to the 5th over 5 plus any constant. Sine of 2x times cosine of 2x times the x with respect to x. All right, what's the move here? Well, hopefully you've caught on to the pattern by now that we're looking for, obviously, like, we're looking for something and then the derivative of that thing both being in the integral, and the derivative of sine is cosine. So maybe I'll let my u be sine of 2x and I'll see what happens. So u equals sine of 2x. So then my du dx equals cosine of 2x, and then I gotta chain rule it, so that's times 2. So then I look back up here and I see my cosine of 2x. I don't see my 2, but I can do just like I did up here, where I basically multiply by 1, but then I put part of the 1 outside, so that there's a 2 inside and there's a half outside in this case. So what that would look like is, well, I could do a half outside, and then on the inside, sine x, sine 2x rather, cosine of 2x times 2 with respect to x. And so now I have my du dx and I have my u, and I just have 1/2 out there to balance out the 2 that I sort of made up here. Okay, I'm gonna get 1/2 integral of, and my u is that sine of 2x. So that's just u, and then cosine of 2x times 2 is du dx times dx. Dx is canceled, I just get du. So all I have to do is unpower rule it, basically. That's gonna be 1/2 times u squared over 2 plus any constant that I like. And then when I multiply that 1/2 out, it sort of just absorbs into the c, because multiplied by 1/2 or not, it's still any number that I want to. So that's u to the 4th over 4 plus any number that I want. So u to the 4th over 4, whoa, u squared over 4. And then I just plug back in so I can get things in terms of x again. So that's sine squared of 2x. Sine x over cosine cubed of x. So this one, on some of these, you're gonna wanna, I realize this may disappoint and or infuriate some, but on some of these you're gonna need to know just a little bit of trig identities and stuff. So sine of x over cosine of x, that is a tangent of x, and then 1 over cosine squared of x is what we have left after that. We would have tangent times 1 over cosine squared. 1 over cosine squared is secant squared. So that would be tangent x, secant squared x. So what are we going to do? Well, if you think back to your derivatives of various trig functions, you see that the derivative of tangent x is secant squared of x. So you can say it's tangent x du dx. I'm going to do this 2 ways actually. Is secant squared of x. So then this just becomes the integral of u with respect to u, which is u squared over 2 plus any constant. Plug back in, that's a half tangent squared of u plus any constant. Now, another way you could do this, you may also see from here, you've got tangent x times secant x, and then you've got times secant x. The derivative of secant x is secant tangent. So I could also say u equals secant x, and then my du dx is secant x tangent x. That also works. So then what I would get would be, once again, the integral of u with respect to u. So then you would once again get the antiderivative of u with respect to u, which is u squared over 2 plus c again. Plug back in, and you're going to get, plug back in, I should be pointing here, and you get secant squared of x over 2 plus c. Now here's the thing. You're looking at this, you're looking at this, and you're thinking those are not the same. Here's the trick. So secant squared, going all the way back to our trig identities, is equal to tangent squared plus 1. Tangent squared x plus 1 over 2 plus c. That's the same thing, right? So then what happens, I don't know why I wrote u here. That should be an x. So then what happens is you get tangent squared of x over 2 plus 1 plus c, but you know, just like 1/2 times any constant can still be any constant, 1 plus any constant can still be any constant. So you can sort of absorb that into the c just like before, and you just get tangent squared x over 2 plus c. So these answers, 2 different ways of doing it, and it seems like you get different answers, but because of the ambiguity with this constant that arises, they are equivalent. So that's the gist of it. You know, practice is really the main thing here. Just practice as much as you can. But this is, you know, the idea is there. You just have to get comfortable with applying the idea in a lot of slightly different scenarios. What timing on that outro? Yeah. Just make sure you're looking for a thing and then the derivative of the thing, both in the integral, so that you can get this sort of nice substitution where instead of dx, you end up with du, and then some other function of u, and hopefully that's nicer to integrate. That's u-sub for you. Practice makes perfect, or permanent if you're an intellectual. And yeah, mealswiththeta.com, hfamealswiththeta.com. Let's not make that mistake again. Goodbye.